Okay, in this video, we're going to be examining graphs again by now looking at their symmetry. So the different types of symmetry we're going to be discussing is line symmetry and point symmetry. Okay, what we mean by line symmetry, the graph can be folded along a line so that the two halves match. Here, we see that we could fold this thing along the x-axis. If we fold in half, that the two sides would match up. Here we can see if we fold it along the y-axis that the two halves would also match up. So the x-axis and the y-axis are common lines of symmetry in a lot of these problems that we're working. Then we have point symmetry. Let me describe point symmetry. Point symmetry says we can take a graph and we could spin it 180 degrees. So if we rotated this, we rotate the whole thing, spin it around upside down, then it's the same graph. This is called point symmetry or rotational symmetry. Now our axis of symmetry here would be the point 0, 0, the origin. So the origin is a common point of symmetry, and that's when we're talking about rotational symmetry or revolving around an axis. So now let's see some tests, how we can tell if graphs are symmetrical. Now these go back to geometry, and we talked about this exact same stuff in geometry when we discussed transformations and when we were doing xy transforms into negative xy and all those. That's all these are. It's the exact same material. So here's our test. To see graphically if a point is symmetrical across the x-axis. For every point xy on the graph, the point x negative y will also be on the graph. So how could we test that algebraically? We simply replace y with negative y. So replacing y with negative y results in equivalent equations. Okay, how do we tell if something's symmetrical across the y-axis? It has y-axis symmetry, as with this second case right here. We can flip it across. For every point xy that's on the graph, then negative xy would also be on the graph. So therefore, we could check that by replacing x with negative x. See here, the 2 points. If both of those points are on the graph, then x and negative x being on the graph would result in the same graph. Now the origin, for every point xy on the graph, then negative x, negative y would also be on the graph, which is kind of a combination of these prior two. And the reason for that is if we go back and look at this, rotational symmetry is actually a combination of line symmetry. If you could take a graph and flip it across the x-axis and then flip it across the y-axis, and it results in the same graph. And the same thing if you look at this part, if you were to flip it over here and then flip it up to here, do you see you get the same graph? So point symmetry is actually a combination of both of these. So if xy is on the graph, then negative x, negative y will also be on the graph. So we can test algebraically by replacing y with negative y and replacing x with negative x. And if this results in equivalent equations, then we're going to have origin or rotational symmetry about the origin. Okay, first example says directions. Use the graph here to determine the relationship that we think is happening. Does it have line symmetry? Does it have rotational symmetry? So then we're going to test it by looking at the graph, and then we're going to confirm it algebraically. We're going to confirm it with one of these tests over here. So looking at this graph, it looks like it's mirror images across that y-axis. So I believe we have y-axis symmetry here. Now the test again for y-axis symmetry is we should be able to replace x with negative x and get the exact same equation, and let's see if we can do that. So y equals x to the fourth minus 4x squared is my original. I'm going to replace that with y equals, replace x with negative x's all the way across, minus 4 parentheses negative x squared. Now think about what happens when you raise a negative to a fourth power. We got to raise negative 1 and x both to the fourth power. So the negative 1 becomes a positive 1, and the x to the fourth stays x to the fourth. minus 4, and again the same thing. What happens when you square both the negative 1 and the x? It becomes a positive 1 and an x squared. So notice that as you replace x with negative x's, you get the exact same equation. So what that means is x and negative x results in the same points. They're mirror images. When x is 2, it's the same thing as when x is negative 2. You get the same y values. So therefore we see there algebraically that this does have y-axis symmetry. Okay, number 2. xy equals 6. You see the graph here. Now this looks like it has rotational symmetry. If we were to spin this thing around 180 degrees, it looks like we would have the same graph back. So I believe that this should be origin symmetry or rotational symmetry. And the test there is take your x times y equals 6. If you're able to, let's put equals there. If you're able to turn that into, take out the x, replace it with negative x, take out the y and replace it with negative y. If this is equal to the exact same thing as the original, then yes, it has rotational symmetry. Well, a negative times a negative would be a positive. So therefore, you could change that to xy equals 6, which is identical to the original. So that does confirm that this has origin symmetry. Number 3, your axis of symmetry is right here. So that would be your x-axis of symmetry. So let's test it. That means that you should be able to take your original graph, 4 parentheses x plus 3 squared, plus you take out y, replace it with negative y, and you should be able to get the exact same equation back. Well, if you take negative y, again, and square it, that means squaring both the negative 1 and the positive y, that would result in y squared there, which does give you the original one back. So yes, that does have x-axis symmetry. Okay, the next one looks like it actually has every type of symmetry. Looks like you could flip it across the x-axis, you get the same graph. Flip it across the y-axis, you get the same graph, and then it would have rotational symmetry as well. So let's test all 3. Okay, we'll start with x-axis symmetry. That means that we can take out y and replace it with negative y. So you get negative y squared minus x squared equals 1. If that gives you the original back, then it has x-axis symmetry. And you see this. When you square a negative y, when you square each part, that gives you a positive and a y squared, which is the original again. So yes, it has x-axis symmetry. Y-axis symmetry says you should be able to take out the x and replace it with negative x. So let's remove this, replace it with negative x, and the same thing happens. Square each, and it does result in a positive x squared. And without even doing it, we already know to check for the origin, we replace both with the y with negative y and replace the x with a negative x. Let me try that again. And square it, and it should give you the exact same equation you started with. And we've already done this. Square each here gives you y squared, square each here gives you x squared, and that will be y squared minus x squared equals 1, which is the original. So yes, it has all 3 types of symmetry. Okay, number 5. Your symmetry here looks to be this. Well, this line doesn't work. That'd be your x-axis. It doesn't flip that way. If you flip it this way, then this would come up here, so that's not going to be right. And since it doesn't have x-axis and y-axis, I don't think it's going to have origin. If we spin it, we don't get the same graph. Looks like it would be if it wasn't moved over 1. If it was right there in the middle, it would have rotational symmetry, so this one would have no symmetry at all. So let's move on to number 6. And with number 6, it looks like we have y-axis symmetry. You can flip it across the y-axis. So again, that means that we should be able to take x and replace it with negative x. So we have negative absolute value of negative x minus 2. And if you take the absolute value of a number, it makes it positive. So the absolute value of negative x and the absolute value of positive x is the exact same thing. So you do get your original back. So therefore, it does check out. Now, something that you don't see much more that you could actually do here, the same way that you can split radicals, you can actually also split absolute values. So the absolute value of negative x could be split into the absolute value of negative 1 times the absolute value of x. To prove that, the absolute value of negative 1 is equal to positive 1, so you have 1 times the absolute value of x. So that's another way you could have worked that problem. Now, even in odd functions, we have special names for these symmetries. Now let's actually apply those names to them. A function is even, we'll start out with, if it is symmetrical with respect to the y-axis. If it has y-axis symmetry, therefore it's going to be considered an even function. The algebraic check, now we've already had one algebraic check that says has y-axis symmetry if you can replace x with negative x. Let's write that in a more mathematical friendly way. If f of x is equal to f of negative x, which means the exact same thing. If f of x, putting x in, is the same thing as putting negative x in, then it's going to be an even function. If replacing x with negative x gives you the same function, it's even. A function is an odd function if it is symmetrical with respect to the origin, or it has rotational symmetry. And combining the test that we did before, here's how you can check to see if something is odd. If f of negative x is the exact same thing as the negative f of x is the test that we can use now, then it's going to be an odd function, which is going to ultimately be the exact same thing as replacing x with negative x and y with negative y. It does the same thing. So now let's check some of these. It says determine algebraically if these functions are even, odd, or neither. If even or odd, describe the symmetry. So to test this, here's your function f of x. So the first thing I like to do is replace x with negative x. So let's take out our x here and replace it with negative x and negative x. Clean it up. A negative raised to a third power. Now, it comes in handy if you'll keep this in mind. Negative x to the second power versus negative x to the third power, negative x to the fourth power. If you just understand what's going to happen in each of these scenarios. Let's do up through sixth power. If you raise a negative x to a second power, that means squaring the negative one and squaring the x. When you square a negative, it becomes positive. When you square the x, it becomes x squared. So it removed the negative. When you raise a negative x to the third power, you've got a cube. You got to raise each of these to the third power. When you square a negative one, it stays negative one. When you square x to the third, it stays x to the third. When you raise negative x to the fourth power, raising negative one to the fourth becomes a positive one. Raising an x to the fourth power, you now have x to the fourth. So do you see the pattern? When you raise a negative value to an odd power, it stays negative. When you raise it to an even power, it becomes positive. So therefore, negative x to the third right here is actually negative of x to the third. Then you have minus minus, which makes this a plus x. So that's what I do first. I always find f of negative x first. Now to find negative f of x, it's really simple. To find negative f of x, that simply says take f of x and make everything negative. So take all of this and make it all negative. So x to the third becomes negative x to the third. A negative x becomes a positive x. And here again is your rules. If f of negative x is equal to the original f of x, it's even. If f of negative x is equal to negative f of x, it's odd. So in this case, since these are the same, f of negative x is equal to f of positive x, it's odd, which means it has rotational symmetry. Without even graphing this, it will have not y-axis, it will have origin symmetry, meaning if you spin this around the origin, you would get the exact same graph back. Number 7. To check its symmetry, let's first find f of negative x, which means take out the x and put in negative x. Make sure that you square it first. So that's going to be leave the negative. When you do negative x squared, it becomes x squared. And we really don't have to go any further because here's f of negative x. And notice that it matches the original. So this would be even. It's an even function, so it has y-axis symmetry. Number 9. Let's find f of negative x, which means let's take out every x and plug in negative x. Anytime it's to an odd power, the negative is going to stay. So that's going to be negative x to the third minus, bring down the minus. You've got to square it first. We raise it to an even power. That means it becomes positive. Then a negative 2 times a negative x will be a plus 2x. So obviously that does not match this. So it is not odd. Let me change colors. Let's check negative f of x. With negative f of x, take your original and change everything to negative. So that'd be a negative x to the third, a positive x squared, and a positive 2x, which nearly matches, except for this middle term. So therefore, it's not even. So this would have neither type of symmetry. Okay, number 10. Step number 1, find f of negative x, which means you take all the x's and make them negative x's. So you now have negative x to the second minus 4 inside here. When you raise a negative x to the second power, again, it becomes a positive. So that is now positive x squared. And you can see already that matches the original. So this has even. It's an even function, so it has y-axis symmetry. And I want to stop on this one. I actually want to graph this and just show you that it would have that symmetry if it were graphed. Okay, so I've taken Desmos and I've graphed this, y equals the square root of x squared minus 4. So you see that it does have that y-axis symmetry. If you were to flip, you can check every one of these points as you go down through here. This point matches with a point over here. This point up here matches with a point over here. For every x that you plug in, negative x has the exact same value. So it does have y-axis symmetry. Number 11. Let's test for even or odd. So first off, let's find f of negative x. The way we do that, take out the x and put in a negative x. And what that does, it changes negative divided by negative would now be a positive 8 over x, which does not match up with the original. So obviously this will not be an even function. Now let's check and see if it's an odd function. So for odd, what we're going to do is find f of, or negative f of x, which means take your entire function and make it negative. So negative, negative 8 over x, negative, negative cancels, makes it positive. So f of negative x actually matches f of negative x. So therefore, this would be an odd function, and it would have rotational symmetry. Meaning, again, you could graph it, and you should be able to spin it around the origin and get the exact same graph back. And the last one, f of x equals the absolute value of x plus 1. Let's first find f of negative x. So let's take out the x and put in negative x, and there's not a lot we can do to simplify that. So let's try negative f of x, which means we're going to take the entire function and make it negative, and you can check that. There's not much you can do with that, and you can plug in values and see that these do not match up, so these have no symmetry.